Welcome to this instructional video about affinity chromatography and dialysis. So, you have a sample of proteins that you need to separate. And this could be for a variety of reasons. You perhaps want to study one protein that may be involved in cancer. You may want to study another protein involved in diabetes. So the heart of biomedical sciences is isolating molecules like proteins so they can be studied by various experimental methods. But the first thing you have to do is get a pure sample of the protein to be studied. So you may have tried ion exchange chromatography or size exclusion chromatography, and those may not have worked as well as you wanted, so you have to be a little more aggressive with it and turn to affinity chromatography. So let's look at our image here. Let's say we have three proteins, and they're going to have the green, the blue, and the red. And they are in an aqueous solution, buffered, and you need to separate them to do the experiments that need to be done. So what you're going to do is you're going to pack a column with a resin, and sometimes we call a resin a matrix. You're going to pack the column. The resin is going to be inert, and again, this is going to be probably a plastic or some type of glass column. All right, and some things about this protein. You have to know some things about the proteins to do affinity chromatography. You know that the red protein likes to bind a certain ligand. And again, a ligand is a small molecule that binds to a protein. And this works because, let's say, the red protein can bind the ligand, which is a black dot in this case. But the blue protein and the green protein cannot, with high affinity, bind the ligand. So what you need to do is take the resin, this inert substance, something like agarose, for example, is something that is an inert substrate or can be an inert resin or matrix, and you need to chemically attach. This is where you need your organic chemistry friends to come in, perhaps, is chemically attach the ligand to the resin, and therefore you have a column packed with resin or matrix, and it also has chemically attached the ligand that will only bind to the red protein. So when you pass the red, the blue, and the green protein over the column, you wash it with buffer, continuous washing with buffer, and so you're going to have, the buffer be coming out here at the column, and you're going to collect what comes out of the column with fractions, glass tubes or plastic tubes in what we call a fraction collector. And so what we know is that the blue and green protein will pass through the column and they will not stick. So blue and green do not stick to the column. They will be washed out with buffer. Why don't they stick to the column? Because there's nothing to hold on to. But the red protein sticks to the column. The red protein has to stick to the column because it has a ligand that it binds to through non-covalent interactions attached to the resin. So the red proteins will be retained on the column. Okay, they will be retained on the column. The blue and the green will be washed out of the column. Ladies and gentlemen, you have just separated the red protein from the blue and green protein. That was your goal. But you are not done yet, because the goal really wasn't to retain or to have the red protein stuck on the column. You now have to remove it from the column. And you should think to yourself right now, how could I remove the red protein from the column into a separate fraction, a separate glass tube so that it will be purified at that point, that I could use it in subsequent experiments. How are you going to remove the red protein from the resin? And again, the resin has a ligand that binds to the red protein covalently attached to it. Well, you may be thinking, here's what people typically think. They think, well, heat it up. That'll get things moving around and get the protein to release. Well, you don't want to be heating a column. You don't want the protein to be denatured. You want the protein to retain its natural structure. Also, you probably thought in your mind, well, we could change the pH of the buffer. Well, you don't want to go to extreme pH values because you don't want to affect the structure of any of the proteins, especially the red protein. The easiest thing to do is to get some free ligand. That is ligand that is not attached to the resin. And start passing it over the column. What you will get is the following. Let's see if I can copy this here. Good. All right. So I'm going to erase the resin from this. And I'm just going to have now red protein with a black ligand. Okay? And what we have, though, is what we have just done is we have released red protein from the resin, or if you want to call it, the column. The free ligand, not attached to the resin, is in competition with the ligand that is attached to the resin. And since there is this competition, and I guess we should draw this equilibrium, then you will always have, and you increase the concentration of the free ligand higher and higher. At some point, you're going to drive the equilibrium to the right. And the equilibrium to the right is red protein bound to ligand not attached to the resin. Therefore, it will just travel down the column and come out into your glass fraction, your fraction tube. This is a way to purify the red protein. Ladies and gentlemen, this is affinity chromatography because the red protein has affinity for the black ligand. The blue protein doesn't, the green protein doesn't, only the red. And we have exploited this affinity in order to first retain it and then release it from a column. So now we have a purified sample of the red protein. Now, one of the issues is we don't want necessarily the ligand bound to the red protein. So there has to be a way that once you purify a protein is to get some contaminating molecules away from it or to release them. This is where dialysis comes in. So in dialysis, you have a beaker, for example, and in the beaker you have some type of aqueous buffer. You may want to keep the pH about 7. And you have a dialysis bag, a membrane bag that you have placed, for example, the fractions from our affinity chromatography. It may contain the protein and it may contain the ligand. In this case, in this image, the blue is the protein. We're changing colors here. So in fact, let's not even connect it to the previous slide. Let's say you have the blue protein and you have some contaminating smaller molecules that you need to get rid of. So the red could be some type of ligand or other small molecules. And you don't want these contaminating small molecules in your solution with the protein. You just want the protein. Now, how does dialysis work? Well, it relies on equilibrium. So the dialysis bag is porous. So this is the big deal. The dialysis bag is porous. Only the red molecules can go through the pores of the bag. The blue proteins are so large they cannot pores in the membrane. So they always stay in the membrane bag, if you will. They do not go into the buffer or the solvent. But the red molecules will equilibrate into the buffer, the solvent. There will be an equilibration. So you put your dialysis bag, probably want to do this at fairly low temperatures to make sure the protein doesn't denature. And you let the red molecules equilibrate between the bag and the buffer, bag and the buffer, bag and the buffer. And then once they equilibrate, take the dialysis bag out, put it in fresh buffer. Let it equilibrate. Take the dialysis bag out, put it in fresh buffer, let it equilibrate. You are essentially removing at each step more and more of the red small molecules, contaminating molecules. It could be the ligand in the previous slide or page about affinity chromatography. The bottom line is you are getting contaminating molecules away from precious protein. So now you have in the dialysis bag, the membrane bag, is you have the protein, and I don't want to say no contaminating molecules, but certainly with a much smaller number of contaminants. Which is a good thing, because the goal was to get purified protein. You want to get these other molecules away from it. All right, this concludes this movie presentation, instructional video on affinity chromatography and dialysis.